equal to K1 divided by K2, which is nothing but a partial pressure of the product divided by partial pressure of the reactant. The delta Ng, which stands for number of moles of gaseous product minus number of moles of gaseous reactant. If the values of the Kc is above the 10 to the power of plus 3, then we can say that the reaction proceed is almost in the completion state. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called equilibrium. Under this unit, we have discussed about the equilibria of chemical reaction, and also we have discussed about the equilibrium in the chemical processes, and also we have learned about the characteristics of the chemical equilibrium, types of chemical equilibrium, and the law of mass action. Today, let us move on to the next topic of this unit by understanding the derivation of Kp expression for the gaseous reversible homogeneous reaction and the relationship between the Kp and Kc we are going to understand, and the application of equilibrium constant and the relationship between the equilibrium constant and with the reaction coefficient and the Gibbs free energy we are going to understand in this session. First, let us see how to derive an Kp expression for a reversible homogeneous reaction, and it is mainly for gases. Okay, so let us consider my reactant A and B, which is going to give a product C and D. Remember, the small a, b, c and d are the stoichiometric coefficient and they are nothing but numbers. Let Pa and Pb and Pc and Pd are nothing but a partial pressure of the gases which are exerted by the reactant as well as with the product. And also I am going to consider, that is V1 and V2 are the velocity of the forward reaction as well as with the backward reaction. So this is a V1 and this is a V2 for the forward as well as with the backward reaction. Now let us apply the law of mass action for the forward reaction. So we know that V1, which is directly proportional to the Pa into Pb raised to the power b. And here the Pa and Pb are nothing but a partial pressure of the gases, and small a and small b are nothing but a reaction coefficient or stoichiometric coefficient. In order to remove this proportionality constant, I will put K1. So V1 is equal to K1 into Pa into Pb. Then what is the Ka? K is nothing but a velocity constant for a forward reaction. So I am applying the law of mass action for the forward reaction as well as for the backward reaction. Just I am writing only for the forward reaction. So V1, which is equal to K1 into Pa into Pb. Now let us apply the law of mass action for the backward reaction. That is, V2 is directly proportional to the Pc into Pd, or V2 which is equal to K2 into Pc into Pd, where K2 is again a velocity constant for the backward reaction. Now we know that at equilibrium, V1 will be equal to V2. And what is the V1? We know that V1 is equal to K1 into Pa into Pb. Similarly, we know that what is the V2 also? That is K2 Pc into Pd. Correct, no? So, this is how I apply the values for the V1 and V2 at equilibrium. Now, I make this equation as K1 divided by K2 is equal to Pc into Pd divided by Pa raised to the power A into Pb raised to the power B. The velocity constant, that is K1 divided by K2, which I call that as Kp. So what is the Kp here? Kp is equal to K1 divided by K2. Then what is Kp now? Kp is nothing but a equilibrium constant, and it is nothing but a ratio of product of the partial pressure of the product to the product of partial pressure of the reactant raised to the power of the respective numbers of the mole. You can see that Kp is equal to K1 divided by K2, which is nothing but a partial pressure of the product divided by partial pressure of the reactant. So what is the Kp? It is nothing but a ratio of partial pressure which is exerted by the product divided by partial pressure of the reactant molecules raised to the power with the respective number of moles. That is said to be equilibrium constant, that is Kp, and this is one of the important derivation for your examination point of view. Hope you all understood how to write with this equation by taking up a single reversible reaction. Now let us see the relationship between the Kp as well as with the Kc. So Kp is nothing but an equilibrium constant which is equal to Kc into RT raised to the power delta Ng. What does this delta Ng stand for? It is nothing but a number of moles of the gaseous product minus number of moles of the reactant. So for example, I taken an example where nitrogen combines with an hydrogen and giving rise to ammonia. Okay. In order to balance this equation, I'll write N2 plus 3H2 give rise to NH3. So, in order to calculate the delta Ng here, which is obtained by what? Number of moles of the gases of the product. So, here we know that my reactant, those two are the gases, whereas my product is also in the gaseous state. Correct, no? Now, how many moles of the gases will be formed in the product side? This is a product as we know, and these two are what? Reactant. Correct, no? So, how many moles will be there? So, there are 2 moles of the product will be there minus number of moles of the gaseous product. We have to see that the reactant. Both are in the gaseous state. So, 3 plus 1, it is 4. So, it is minus 2. So, what is the delta Ng value for the above reaction? It is minus 2. This is how you know the delta Ng value can be calculated for the given equation. I'll take up one more reaction so that you'll understand how to write up. That is calcium carbonate. It is a solid which is decomposed to give calcium oxide plus carbon dioxide. So again this is a solid and this is a gas. Correct now? How to write the delta Ng value? Delta Ng value will be obtained by the Ng of product in the gaseous state minus Np of the reactant in the gaseous state. Now if you see that how many products will be there? So there are 2 products which has been formed. In that only we have to consider the gaseous molecule. Why it is only the gaseous molecule? Because in the definitions we have understood that the delta Ng, which stands for number of moles of gaseous product minus number of moles of gaseous reactant. We need to see only the gaseous reactant as well as with the product. Even though my product is consists of one is solid, one is gases, I need to consider with the only one because only one gaseous product will be formed. So it is 1 minus, you can see that in the reactant side, you know, nothing which is there because it is only the solid state. So I cannot consider, so it is nothing but a 1, that is a delta Ng value. This is how you know only the gaseous molecules will be considered, that is with the reactant side as well as with the product side, and then you subtract, you know, you will get the value of delta Ng, and this is the relationship between the Kp with the Kc, that is Kp is equal to Kc into RT to the power delta Ng. Now let us see how to write the relationship between the Kp with the Kc with the following reaction. It is very important for the examination point of view. It can be asked for 2 to 3 marks. So we'll take up one example. Okay. So nitrogen combines with the nitrogen which forms a ammonia. Now how to write the relationship between the Kp with the Kc. Okay. First I'll calculate the delta Ng, that is nothing but a 2 minus 3 plus 4, that is 3 plus 1, that is 4, which is equal to minus 2. We have a relationship with the Kp and Kc, that is Kp is equal to Kc into RT to the power of delta Ng. Correct, no? So if delta Ng values is minus 2, what will happen? So the Kp is equal to Kc divided by RT to the power of minus 2. I am rewriting this equation also like this. Now, from this above equation, it is clear that Kp is smaller than the Kc, or you can say that Kc is greater than Kp. Okay, this is how, for the given reaction, we can rewrite the relationship between the Kp with the Kc. We'll take one more example, that is PeCl5, that is phosphorus pentachloride, which is upon decomposition, which is giving rise to PCl3 plus Cl2. Delta Ng for this above reaction is, so you can see that both are in the gaseous state. So how many products will be formed? 2, and then 1 plus 1 is 2, minus 1 because this is my reactant which is also 1. So it is equal to 1. Now what will happen to the above equation? Kp is equal to Kc into R to the power of 1. So anything raised to the power which is equal to what? RT only. Correct, no? So Kp is equal to Kc into RT. So from this equation it indicates that the Kp value, that is the equilibrium constant value, will be greater than Kc value. We'll take up one more reaction, hydrogen iodide, which is upon decomposition it gives rise to the hydrogen plus iodine. Let's see how to calculate with the delta Ng value. Since only 2 products will be there and both are in the gaseous state, 2 minus 2 which is equal to 0. Now delta Ng I got it as 0, then the above equation will become Kp is equal to Kc into the R to the power of 0. So anything raised to the power will be equal to 0 only. So from this equation which is indicates that Kp will be equal to Kc. This is how we can write the relationship between the equilibrium constant with the Kc by understanding the number of gaseous product minus number of gaseous reactant. Hope you all understood with this. We'll see with the next one, that is relationship between the equilibrium constant for a general reaction and its multiples. So here I am taking a general reaction where A plus V is giving rise to C plus D, and the stoichiometric coefficient are small a, small b, small c and small d. Now for this reaction we know that the equilibrium constant will be represented as K. Suppose if the reactions are coming from the backward direction, that is from C plus D is going to give for A plus B. Okay, again these are the reaction coefficient. Okay, so here for my first reaction it is a forward reaction. This is a backward. So for the forward reaction, we have the constant value, that is equilibrium value as K. Whereas for the backward reaction, Kc value will be become 1 divided by, that is Kc value. Why it is 1 divided by Kc value? Because it's a backward reaction. In the forward reaction, we got it as only K. Coming into the one more reaction, I consider my first reaction and I'll multiply it with an N. So what will happen? N into A plus N into B, which is giving rise to N into C plus N into D. So how to write the Kc value? Kc double dash, which is equal to Kc to the power N. This is how the equilibrium constant value can be multiplied with the or can be written with the various general reaction. Next we will see the application of equilibrium constant. So after understanding what is the equilibrium constant and how to derive a equation or expression for the equilibrium constant, we need to understand where exactly we are using this equilibrium constant. This equilibrium constant will be used to understand or used to know the extent of reaction or used to predict for the extent of reaction, and it is used to predict the direction of the reaction, and it used to calculate the equilibrium concentration. Okay, these are the three main applications of the equilibrium constant. We'll take up one example so that you will understand that how this equilibrium constant, it helps us to predict the extent of the reaction. The equilibrium constant, we know that it is directly proportional to the concentration of the product and it is inversely proportional to the concentration of the reactant, as we have already understood. And it shows that higher the values of K, faster will be the reaction and nearly it will be completed. But smaller the values of K, slower will be the reaction and reactions will be proceeds rarely. We can understand this by looking at this figure. So here I have written the Kc value, that is the equilibrium constant value. If it is an 1, okay, both the reactant and the products, they are present at the equilibrium state. If it is below than 1, that is 10 to the power of minus 3, this indicates that the reaction is hardly proceeds. Okay, this indicates that the reactions which is hardly proceeds, in the sense either the reactants are not completely converted into product or some of the reactants can already forming a product. Okay. If the values of the Kc is above the 10 to the power of plus 3, then we can say that the reaction proceed is almost in the completion state, which indicates that how many moles of the reactants which is there in that reaction conditions, which is completely converted into product, thereby, it attains a particular stage of completion. This is how, we can predict the extent of reaction by using a Kc value, that is equilibrium constant value. It predicts the direction of the reaction. How does this Kc, which also helps us to predict the direction of the reaction? We'll see now. It helps us to predict the direction of the reaction of any stage by using the reaction coefficient, that is Q. Okay. So, by using a reaction coefficient Q, it helps us to indicate in what direction the reactions are going on. Okay. The reaction coefficient Q, it is nothing but a concentration of the product divided by concentration of the reactant, and it is same for the equilibrium constant, except the concentration is not negligibly equilibrium values. As we have understood that Q is nothing but a concentration of the product divided by concentration of the reactant, as we have seen with the Kp value also. Correct, no? If Qc which is equal to Kc, the reactions will be proceeds to the left, that is to the reactant side. If Qc is lesser than Kc, then the reactions will be proceed to the right side, that is towards the product. So, it is from the reactant side and this is towards the product side. If Kc value, if it is equal to the Qc value, then the reaction mixtures will be attains the equilibrium, so that the rate of forward reactions will be equal to the rate of backward reaction and there is no net reactions will be occurs and that system will attain the equilibrium. This is how the reaction coefficient Q or Qc will be expressed in order to indicate the directions of the reaction. Next, we have relationship between the equilibrium constant, reaction coefficient as well as with the Gibbs free energy. We already understood that what is the Gibbs free energy in your thermodynamics. Correct, no? So, how does it related to equilibrium constant as well as with the reaction coefficient? We'll see now. We have a relationship, that is delta G is equal to delta G naught plus RT ln Ke. So, here at equilibrium, I am considering delta G will be equal to what? 0. Then Kc value will be become what? Qc. Then above equations will be equal to two conditions. One is if delta G is lesser than 0, then the Kc value will become greater than 1. It shows that the reactions are going in a forward direction, that is in the spontaneous processes. So that reaction proceed in a forward reaction and more quantitative of the product which has been formed. Suppose if the delta G naught values are greater than 0, then Kc value which is also it has become lesser than 1. In such cases, we say that it is a non-spontaneous process and it is nothing but a backward reaction, and it minimizes the very minute quantity of product which has been formed. This is how we can relate the Kc, that is the equilibrium constant, and the Gibbs free energy along with the reaction coefficient. In the next class, we are going to understand more about the factors which are also affecting to the equilibria. Hope you all understood with this session. I'll come back with the next topic. Till then, take care, be safe. Thank you.